Welcome back to our Chem 1331 lecture series. We're getting close to the end of the term, and we're still talking about Chapter 9 in Zundal, and today's talk is going to discuss solids, the solid state, types of solids, introduction to structure, and so forth, and the like. And we'll continue this next week and discussing the electronic properties of solids and metals and things such as that, metal insulators and semiconductors, and we'll get through Chapter 9, and that will be our last part of the course. So again, this is the Chem 1331 Chapter 9. And remember to click subscribe and like for one extra credit point. Not too many people are doing this, so this is a great opportunity for those of you that are. If you're not doing it, well, I don't understand why you're not. This is your tuition dollars going down the drain, I guess, but that's your call. I hope you're all doing well and staying safe and maintaining your social distancing and all that kind of stuff. So in a solid, in the solid state, if we look over at our lattice structures that I have over here on the left, the thing that differentiates a solid from a liquid is essentially, as we mentioned before, a liquid will, like for example, my little bottle of hand sanitizer here, the liquid will conform to the volume that it is placed in, and you will have and it moves, it flows, and so on. We're all familiar with those properties of liquids. A solid does not do that. So you could describe the plastic that is on the outside of this as a solid. It responds, it pushes. As I push against it, maybe it deforms it a bit, responds, it bounces back to where I was. And there's different kinds of solids. I could describe, the plastic on this is a solid, the paper is a solid, and different solids have different properties. In fact, if I look at the atomic level of a solid, what I notice is that the atoms in a solid are placed at regular and defined places. So this is a very small cluster of atoms that from a calculation that we did. But you can see, for example, in the arrangement of the spheres around this particular solid, you can see a regular hexagonal pattern. For example, I'm highlighting here a regular hexagonal pattern, and maybe over here I have another kind of facet. I have another kind of packing, but in this very small segment of a solid, this is actually from a cluster, there's a regular packing that's defined by the interatomic and intermolecular forces that are keeping this together. Okay. Now, different kind of solids have different packings of the atoms, and you can see some evidence of this already. You can see maybe a layer here of this hexagonal layer, and as I move down, maybe here I have a different kind of packing arrangement, different kind of packing arrangements of this cluster. And I think this was 141 individual balls that were packed together, minimizing the energy. And this was from, like I said, a calculation that my student did a number of years ago that we printed out with a 3D printer just because it looked really cool. Okay, but if I look over there to the PowerPoint slide that I have, you can see that I can arrange four or I can arrange these atoms in what's called a unit cell. And the unit cell is the minimal repeating unit that defines the solid. So you could, like for example, on my background here that I have a grid, and so I could define maybe this little square as the unit cell, or maybe this bigger square as a unit cell for defining the grid on my desktop here. So I could go 1 unit cell, 2 unit cells, 3 unit cells. And so I could define, if I knew I had an atom here, I could say, well, I'm going to move 1 unit cell or 1 lattice direction away. I will find another atom. I can move one in this direction and 1 in that direction, find an atom, and so on and so forth. Or I might have another unit cell that has here and here. Maybe I have a different atom here than I do here. Well, I can move here and find that atom, or I might move to here and find that atom. Or I could even have another kind of unit cell. Maybe I have an atom here and another kind of atom located at this point and this point. And so as I move from this point to that point, I find atom A to atom A. Maybe I can denote that with maybe a coin. So maybe I have like that coin here, and I have another coin. Let me get another coin. So, for example, maybe I have a lattice that's made out of nickels and pennies. So I have a lattice of nickels that I could put here. Maybe I have a penny that I place here. Let me get 2 more nickels. So I could have a lattice, for example. Maybe I put my nickels at each site like this. Okay, and I could have a packing arrangement of those nickels like that. But maybe every once in a while I have another lattice that might be something like this. This is of course a 2-dimensional lattice, and maybe I have pennies that are going in between, something like this, and another one here, and another one here. Okay. So you can see I can arrange pennies and nickels or different kinds of atoms if I want in an arrangement. So if I place all of these nickels at regular intervals, you could predict, well, if I move 1 lattice direction in this direction, well, maybe I should find a nickel, also another nickel right there, right? And I could continue this on infinitely. And likewise with my pennies, if I know that I have a penny here, I have a penny here, well, maybe I can find another atom. Let's put my nickel back to there. I would have another penny, evenly spaced along in that lattice direction. Well, you can't see that very well. Along in that lattice direction, okay? A little too much shine on that. Maybe like right there. It's a little easier to see. Okay, so this defines what's called a lattice direction. This is the lattice direction in that direction. Here's the lattice direction in that direction. And if I were to continue this on in 3 dimensions, I could have a lattice direction, a lattice vector in this direction. And so here I have 2 interposed lattices of pennies and nickels, and or I could call this atom A and atom B, and I can continue this on in 3 dimensions as well. And that's what we do over here, over there on the left. I can imagine I have a simple cubic lattice. Well, let's say I put each. Let's imagine that the square that I have defined as 1 lattice vector, or as 1 lattice, and I put 1 nickel at each of the atom sites. Okay. Now, of course, I would have to have another layer of this directly above, but it's hard to do this and make nickels float, I guess. But you can see in this particular lattice, I have in this lattice cell, which I can define as this square, I have 1/4 of a nickel here. I have 1/4 of a nickel here, 1/4 of a nickel here, and 1/4 of a coin right there. So I have 1 whole coin in this unit cell. So I have 1 whole coin. So even though I have 4 nickels at each lattice corner, I have in each lattice cubic cell, unit cell, I have 1, and only I have effectively 1 full coin. Now if I had another nickel, Okay, it's not a nickel, it's a quarter. It's a Canadian quarter. I just got back. I was in Canada recently, so I have a bunch of these. So if I put a coin right here in the middle, well, now I have 2 coins per unit cell. So one whole coin that's not cut up, and I have 1, 2, 3, 4 coins that are cut up into 4 corners. So you have one corner of that, one corner of that, one corner of that, one corner of that, for one full coin. And likewise, if I were to have, let's add cells that are here. So this is what is called a body-centered cubic. So if I were to take this coin and put it in the middle of the unit cell, float these 2 guys up in the air, like what I have off to the side there, the body-centered cubic, I would have one spherical coin in the middle, and 1/8 of the coin here. One little corner here. That's 1/8 of a chord of a circle or a sphere. 1/8 of a sphere. 1/8 of a sphere. 1/8 of a sphere. 1/8. 1/8. 1/8. 1/8. So 8 corners give me one full atom inside the unit cell, and one full atom inside the unit cell in the body center. This is called a body-centered cubic unit cell. Now you can also have a face-centered cubic cell, and that would be taking, let's say like an atom. Let's ignore the fact that these are pennies for the moment. Where's this one from? This is from, that's from the UK. Has a picture of the Queen on it. There we go. There she is. You can see that. Here's another picture of the Queen. So in the UK, they use a little bit younger picture of the Queen in the UK than in Canada, I guess. So here's another body-centered site, a body-centered site. Excuse me, this is a face-centered site and a face-centered site. And likewise, I would have these face-centered coins, and actually I need 1 or 2 more. I would have another face-centered site right here in the bottom. Okay, so on this, so each face of this cube that I would have, like you can see drawn over here, each face of the cube in this face-centered cubic, I have 1/8 of a coin. So here, if it's a 2-dimensional face-centered, that would be something more like this. This is a 2-dimensional face-centered cube. I would have, this would be the 2-dimensional face-centered cube. I would have, or face-centered cell. I would have 1 quarter, 1 quarter, 1 quarter, 1 quarter, and in a 3-dimensional case, I would have 1/8, 1/8, 1/8, 1/8, 1/8, 1/8, 1/8, 1/8 on each of the corners of the cube. And each of the face of the cube, I would get a half. So you see, I have one full atom from the corners, and I have one half, one half, one half, one half, one half, one half. I have a total of 1 half, 1 half, 1 half, and 1 half, or 2 on these outer faces, and 1, like a half and a half on the top and bottom faces. So I actually have 3 atoms per unit cell. 3 on the faces, and 4 atoms per unit cell. So it's a little tighter packing arrangement. And that's important. Is that right? 3 atoms per unit cell. I have 1 half, 1 half, 1 half going around. So 1, 2, 3, and 1. So I'll make sure I get this right. I have 1, 2, 3, 4. I have 4 atoms per unit cell in the face-centered cubic. Face-centered cubic. Now, in different metals and different atoms will have different cubic packings. And it's important that we can understand the properties of these different metals by looking at their packing arrangements. Next. Okay, so in the if I look at this in a space filling model, which is what we've drawn over here, you can see this full on. Here's 1/8, one segment, one segment, one segment. So I have a half of an atom here and a half of an atom here. So you can see how that's 1/8. It's not a quarter. It's an eighth. Or excuse me, excuse me. I take all that back. That is that is 1/4 of an atom. So 1/4 of a cell here, 1/4, 1/4, 1/4, 1/4. So I have, if I take these two halves, I get a half, and a half is one. No, I'm sorry. That's an eighth. 1/8 of a segment. 1/8, 1/8, 1/8. It's one atom. Here, in the corners, I have eighth of 1/8 and 1/8. So I have the full atom here sliced up on all the corners, and then a full atom here in the middle. And in this particular case, I have 8 vertices. 1, 2, 3, 4, 5, 6, 7, 8. One atom like this way. And then I have an atom sliced in half on each 1, 2, 1, 2, 3. So it's like I have three atoms sliced in half, stuck to the faces, or I have 4 atoms per unit cell. So 1 atom per unit cell, 2 atoms per unit cell, 4 atoms per unit cell. So polonium, uranium, metal, 1 atom per unit cell, 2 atoms per unit cell for body-centered cubic, 4 atoms per unit cell for face-centered cubic. Okay, now the way you can determine and analyze this crystal structure is by scattering X-rays from a solid surface, a solid object, a solid crystal. So it's important to go through like how this occurs. So first of all, the X-rays basically scatter elastically from the atom sites, and insofar as the X-rays are concerned, the atoms are really small spherical units, small points that bounce off. And let me just show a picture about how this is done. So it is determined in the following way. So imagine that I have a surface, or I have some sort of site, and I'm bouncing X-rays off of this. There's an incoming X-ray at some wavelength, and I have outgoing X-rays, and it's elastic, so this incoming wavelength is the same as this outgoing wavelength. And I have multiple X-rays that are bouncing off of this, and I have multiple X-rays that are bouncing off of this. But the fact is, you see, this X-ray might have had a slightly longer path length. So if I look at the path length of this X-ray versus the path length of this X-ray going up to some sort of detector over here, okay, the path length of this X-ray, this photon, is a little bit longer, or maybe a little bit shorter than that of this photon. And there's an angle that I scattered to, angle theta. And so what I can do is I can use this, I can count up the number of X-rays that are the number of wavelengths that are in each one of these little slices, and look at the difference in wavelength between this photon and that photon arriving at the same point on my detector. And if I do the mathematics, what I find is that n times lambda, the wavelength, is equal to 2d sine theta, where n is an integer, lambda is the wavelength of the photon, okay, and d is the distance, but is sort of the difference in the path length, how far each photon traveled, which is equal to the distance between atoms. Okay, so in other words, if I know this angle, so I know this angle because I can set that up as an experiment. I can put my detector at some angle. I mean, this is easy to determine, but just as the normal degree of freedom. I know this is where it's coming in. I look at the scattering in that direction. This is the angle that I look at, and so it's easy if I know the wavelength I know, and I look at the number of the diffraction peak. And so what I wind up getting, because of the fact that this path length is slightly longer, or maybe slightly shorter than the other, I get constructive and destructive interference at the detector And so I get a series of peaks. I might get a peak like this, and I might get another peak over here, another little weaker peak, and likewise off to the sides. So I know that by looking at this distance, I can transfer. So this is the distance that I would get on the screen. The interference fringes between where I would get constructive and destructive interference, I can relate this distance to n. I know this distance, and I can back out this distance between the atoms. It's very easy to calculate. Well, here's a little bit of a sketch of what I got. You can work this out very readily in terms of just some basic geometry. Really, is what it boils down to, and this Bragg equation, which tells you this relationship. And you can see. So the issue is that these two reflected rays arrive at the same point on a detector screen, and so consequently they have a slightly different path length due to the fact that they scattered off different atom sites. And by analyzing that kind of data, I can pull out the different spaces between the atoms. And if I look in different directions, I will see different diffraction patterns. For example, I can look in one direction and get maybe this spacing. I can look in another angle and get this spacing, and so on and so forth. And so I can pull out and look at by looking at the X-ray diffraction pattern, I can understand the structure of a material. Okay. So, for example, okay, and this angle then is critical. So if I look at if I look at X-rays are scattering from an aluminum crystal, for example, I have 1.54 angstroms. Now the key to understand how this works is that you need the wavelength of the incident light to be comparable to the distance that you're trying to measure. If it's too short or too long, you will not see the diffraction pattern. So, for example, if I tried to use ultraviolet lights, I would not see this diffraction pattern, and it would not be useful. If I tried to use something too short of a wavelength, higher energy X-rays, I would not see anything. Higher energy like gamma rays, I wouldn't see anything either. So you need to use photons that are the right wavelength for trying to measure this spacing. So we can easily work this out. We see the first Bragg peak. It would be nice if they actually showed some data for this. And so I can use the Bragg equation. Let's go back to the Bragg equation. The Bragg equation (2d sine theta), and so our data is that we had theta is equal to 19.3 degrees. We'll look at the first Bragg peak. Lambda is equal to 1.54. Okay, so that means I simply need to. So that means that the sine of 19.3 degrees is just to convert that really quickly. You need to make sure that your calculator is in degrees and not radians. An easy way to check that is so the sine 19 point is 0.3305 is the sine of 19.3 degrees. It's not 19.3 radians. The difference, just so in case you forget, the difference between degrees versus radians is the following. A degree is if I took the circle and cut it up into 360 segments is 1 degree. Is 1 over 130 and 6 of the circumference, or the 360 degrees around the circle is equal to the gives you the radius of the unit circle, or the circumference of a unit circle. A radian is such that I have 2 pi radians go around the circle. So 360 degrees is equal to 2 pi radians. Okay, just as a quick way to understand it. So the issue is if I put in 19.3 and my calculator is set up to do a calculation of radians, I'll get the wrong number. So make sure that your calculator is set up. This must be in degrees. Okay, you can use radians. You can convert 19.3 to radians if you wish, but it's important that you make sure your calculator is not set up that way. Okay, so we can easily do this. Solve for D. And D signs right like that. Just simply rearrange things, and now we can plug in numbers, and you can do this, and you get something that's shown off to the side. 2.33 angstroms, or 233 picometers. Generally, the literature probably uses angstroms more than picometers. But the book likes to use SI units whenever possible. Okay, so there are different kinds of, so that's how we can experimentally determine the size and spacing between atoms in a crystal. So this technique is used extensively in materials characterization. In fact, it's used in proteins to the extent that you can take a very complicated biomolecule like a protein and do X-ray spectroscopy on, or X-ray diffraction on a crystal of a very complicated system, and it's a more complicated analysis clearly, and pull out the spacing between atoms in a very complicated system. Okay, and it's a routine chemical analysis, structural analysis methodology. So we have an X-ray crystallography laboratory, and it's done all the time. Or if we need something more exotic, we can go to a synchrotron and do X-ray scattering. Now, the property of a solid is determined by the interatomic forces, obviously, and there are really three there are multiple kinds of crystalline solids. What's called an ionic solid, for example, sodium chloride is an ionic solid. The atoms in sodium chloride are held together by our ions in sodium chloride, NaCl. What I have are very small sodium plus ions, and I have a chlorine minus ion, and these are all in a nice unit cell. This is, you can already sort of see how the structure of this is going to have to be. Oops, let me make sure I get this in the right. So I need a sodium in between each one of these. So basically, that I have each sodium chloride. So I could take this unit cell and chop it up, for example, like this, and I would have a 1-for-1 sodium chloride match. So the charge, the net charge of the unit cell is neutral. So in the sodium chloride or rock salt crystal structure, the net charge of a unit cell is exactly 0. So I have to have the same number of ions, positive ions, as I do negative ions. Otherwise, I would have a buildup of charge in the system. Molecular solids are systems in which each lattice site, instead of being at an atomic site, is possibly a molecule. For example, anthracene or naphthalene is another example. Anthracene is this molecule. Anthracene is this molecule. Okay, this is anthracene. And anthracene will form a herringbone structure along in one direction. So if I look at this as an edge, I would have a packing of this molecule, something like this. So this is looking down at the edges of this molecule. I can't quite draw yet very well. I would have sort of this herringbone structure of anthracene. So this is sort of like looking at the edges of the anthracene. So along this edge here is if I have two anthracenes that are stacked, sort of like pancakes on top of each other. I can't draw this very well, but let's imagine each one of these little planes are two anthracenes that are sort of like stacked, like this, relative to each other. So like two anthracenes. Here's an anthracene. Here's an anthracene. Sort of like pies. It's stacked on top of each other, and so it's I can slide very easily in this direction. In fact, they're slightly offset like this, and then the next one sort of comes in this herringbone structure. So I have this like T here and another here for forming this like herringbone structure for the anthracene, and that defines a molecular solid, and an atomic solid is where I would have the atoms at the lattice point. So molecular solids have the molecules are at the lattice points, and an atomic solid, I have the atoms are at the lattice points. So metallic solids, network solids, all sorts of different kind of solids that can form. Okay, so an atomic solid, for example, is carbon. So over here is the diamond structure for carbon, and it's I think this is a face-centered cubic cell, and each of the lattice points, so that the cell itself is defined by the sp3 hybridization of all of these carbon atoms that form this network, and it's a lattice, and it forms this beautiful high symmetry diamond. You can have what's called a rock salt configuration. This is what I was trying to draw before, where I have at each of these corners. If you look closely, let's look at the chlorines. This is what solid would we call that? That is a face-centered cubic system, right? So you can see 1, 2, 3, 4. I have the chlorines at the corners, and I have a chlorine at each of the middle of each of the faces. And then likewise, if I look closely, I have for the sodiums, I have also a face-centered cubic solid, because I could, if I took this thing and translated it by a little bit, you can see I would have to have a sodium ion here, and here. And again, it's just like I have two interconnected face-centered cubic crystals, but the corners of one are the sodium chloride, and the corners of the other are the chlorine. The other corners are the sodiums. And so, if I wanted to, I could say, well, here's my repeat cell. I have to have one full repeat cell, because I see if I took this small system right here that have 1, 2, is that little corner right there. And if I define that as my unit cell, well, I can't do that, because if I translate up by one unit cell, that would take this chlorine and put it here. I can't do that. So I need to have this chlorine go all the way up to here to define the unit cell. So the unit cell is defined by, if I were to translate this entire cell up by one unit cell, it would look the same. All of the atoms would superimpose on top of each other. Ice is another is a molecular solid as well. in which case you can see this nice, beautiful, open structure, this sort of hexagonal structure for where the oxygens happen to be with a hydrogen bonding network. Actually, ice is a complicated system because again, as I mentioned from the last time, the positions of all of these hydrogen bonds are a little bit fluctuational, and gives rise to some of the interesting properties that we have for ice. But this is a molecular solid. The molecular positions define the lattice points rather than the atomic positions. Okay, so typically, we can define a metallic versus a network solid. The metallic systems, metal is an interesting bonding network, and if we want, we can do a little bit of the mathematics of that. It might be instructive, and you might find it useful to understand why metals form, why some systems form metals, and we'll talk about that in just a moment. But metal atoms, metals are metals because the valence electrons, for example, here's a metal. Here's a nice big shiny metals, chunk of stainless steel. The electrons that are in this metal are very delocalized. The valence electrons are very delocalized and are sort of shared amongst multiple atoms in this system. Excuse me. The allergies. In a network system, I have, like in, for example, diamond, I have directional covalent bonds, such as in diamond, leading to basically giant molecules. So like you could almost imagine a diamond as being one gigantic molecule. I can't really stop building this thing. It just keeps going as one gigantic full-on molecule. Here's a little cluster of a diamond. But I could continue building this diamond molecule out as far as I want. So it's almost like a network solid is one gigantic micro-sized molecule. And then in group 8, for example, rare gases and such, et cetera, which is what this is an example of. This is from a calculation, like I said, of neon that we did a number of years ago. And the forces between these atoms are simply the London dispersion forces that bound this thing together. And so it forms this more of a, as if I was simply packing marbles together and to form a solid. So the closest packing, pause for a second here. I guess I'm still recording. Okay. So in a, hopefully I can edit that out. In the closest packing model, we assume that the atoms are arranged in a way that the atoms themselves are hard spheres, as if I'm taking like my coins, and I'm assuming that these are hard spheres, hard disks, and I can't mush them together anymore. So the closest packing arrangement, if I want, of pennies or coins like this would be something like in this. Well, they're not quite all the same size in this. Maybe if I have 2, 3, 4. Here's a closest packing arrangement of pennies. Let me get some more pennies. Okay, so these are, I must be in my layer of foreign coins. Okay, so these are 2 pence coins. So a closest packing arrangement of these coins might be something more like this. You can see, so I can pack in this hexagonal packing of these coins like this, and that's as close as I can get all of these coins together. So if I pack like this, that's not close packing. Okay, that's not the closest packing. The closest packing arrangement is in this sort of hexagonal packing arrangement. See, I can form, if I have one more and take this guy around and put another coin here in the middle, I would have the hexagonal closest packing arrangement going around those coins. So see here, 1, 2, 3, 4, 5, 6, one guy in the middle, and now I can have different layers of this closest packing, and so you can see this close packing arrangement on the surface of this cluster. Here's the 6 atoms that I would have here, and I can put another layer on top of these. If I had little balls, I can say, well, maybe my next layer lies on top, and forming on these on this. I'm going to form another layer of coins on top of this. So I could put maybe another. Let's see where I would put it. One layer here, one layer there. I could put another layer, for example, right there. And now I've got the choice of where I put the next layer of coins. So I could put a coin layer either on top of that, or I can put another layer off on where off. You see, if I put a coin layer on top of this, that's still close packing. See, notice I put this layer right on top of. See, here's a little pocket that I can sit a sphere on. So I could sit it like right here. I could sit it right there. Okay, and that's called an A, B. Oh, let's get this arranged right. So I can sit this right on top of there. I guess it's an ABA lattice. So in other words, this third layer is sitting directly on top of the first layer. So it's identical in its packing to the first layer. Here's the first layer, second layer, third layer. So this third layer atom lies right on top of where the first layer atom would happen to be. Or I can set it off to the side here. See, I've got another little pocket. You notice that I can put things. I could actually put here it's centered. So I could also put an atom right here. See, if I put an atom, maybe I see, I can, because there's always going to be another. I can also have a hole right there. See, I can also put a instead of putting it on top, you see, I can put an atom right here in this little pocket, and now you notice that I have an A layer, a B layer, and a C layer. So I have 2 equivalent close packing arrangements called ABA packing, where this third layer sits on top of the first layer, or I have ABC packing, where the third layer sits on top of this little interstitial area. See how there's a little pocket looking down underneath there? There's a little pocket right there, and this atom can sit right on top of that. That's a third layer. Different layering of these atoms as I build up these atomic layers. Okay, so here the second layer is like the first layer except it's displaced. The third layer occupies this little space right here, so you can see how this little pocket lies right on top of that. Well, that's another layer that I can do. So if I can either put it here or I can put it right there in the middle. And these are 2 different structures. These are called hexagonal closest packed structures. Hexagonal. C hexagonal closest packed structures, okay? And there are two. There's an ABA or ABC. And when the spheres are ABA closest packed, it's called a hexagonal prism. And here's another view of that with computer rendered spheres. The top view for the ABA, you can see the next layer sits on top of the little interstitial sites, and then I put the next layer on top of, right on top of where the first layer happened to be. So I have an A layer and a B layer, and the two are just sort of like stacked up like that, and that forms the hexagonal prism. Now I can also have here's the ABA, and you can see that the ABA layer forms what would be something like a body-centered cubic arrangement. So here's this thing in the middle, and so on. Now you can also have the ABC packing, where I have, like I had arranged here, where I have the third layer is sitting like in that on top of a site like that, rather than on top of the site like that. They're equivalent, but they form different packing structures. In the ABC, so ABA gives this hexagonal prism, and the ABC gives cubic closest packed. Okay, it's a face or face-centered cubic. Now, the key is, what's amazing about all of this is that these structures persist out to macroscopic dimensions. And so something that has hexagonal closest packing at the atomic layer is going to look very hexagonal in its crystal structure. The final crystals are going to look hexagonal. And likewise, if you have something that's cubic closest packed at the atomic level, it's going to look cubic in its crystal structure. And this continues on and on and on. Okay, so common characteristics of the HCP versus other packing. So for example, each sphere in both structures possess 12 equivalent nearest neighbors. So if I sit here in the middle and I look around me, I have 12 nearest neighbors that I'm in contact with, 6 on this layer, 3 above me and 3 below me. And the net number of spheres is determined by how many full spheres are inside the unit cell. So for example, this is what I was talking about before. Imagine that I took this face-centered cubic cell and sliced up all the little spheres, and I would have half of an atom on each face. And so I have 6 faces, right? And I have 8 corners, each with 1/8 of an atom on each corner, and I get 4 total atoms inside the unit cell. And likewise, if I know the mass of an atom and I know the volume of the unit cell, I can calculate the density. Right? So if I know the radius of a silver atom, which defines the packing distance between sodium atoms, or silver atoms rather, and I can get the density. So first of all, I need to find the volume of the unit cell and the net number of atoms that it contains. So what do we know? So this is a cubic closest packed structure, and what do we know? So we can say, first of all, we have to let's sketch this out and see how this comes about. So closest packed solid. Let me get rid of all my coins here. Okay, so on this particular solid, the atoms touch each other along the diagonals of the faces, but not along the edges. So that means in this face, this is it's a cubic closest packed structure. This is a face-centered cubic. The atoms touch each other on the faces. Cubic closest packed solid is this FCC. So in this center, so I would have an atom here. Let's just see how this comes about. One atom here, one atom here, and one atom here. Okay, so I only touch the atoms on the diagonals. Okay, so if here is the radius of this root. So here's a radius, and here's a radius, here's a radius, and here's a radius. Okay, so I need to have, here's that D. So the length of this diagonal so here's this diagonal. So here's one whole atom through here. I can't draw that very well. And half an atom here, and half an here. So here is a radius, a radius, a radius, and a radius, right? This is looking along the diagonal of one of those face-centered cubics. So the length of this diagonal is 4 times the radius of that. Now I need to know the size of the unit cell. We'll call this guy D, and that's D. So 4 times radius squared, Pythagorean theorem, is equal to D squared plus D squared. That's Pythagorean theorem. And I get that this D, this distance right here, which is not equal to 2r, this is 4r across here. The atoms only touch each other across the diagonals of these faces. So D, it's simply solving the Pythagorean theorem, or is r times the square root of 8. That we have from over what we can see on the side there. So just very simple geometry allows us to get to this. So of course then the volume is D cubed. Okay. So this radius r is for silver 144 picometers, which was the radius. So the volume then is the this thing cubed, and if it's and remember, if it's a face-centered cubic, how many atoms? 4, right? For face-centered cubic. All right. So if I know the mass of the silver atom, I know the volume D cubed, I can get the density. Right. So we can keep going. So D is 407 picometers. The volume is 407 cubic picometers, and so I can do this calculation very easily, converting this to cubic centimeters if I wish, or keeping it whatever SI units I want to use. Again, I can look at 4 atoms per unit cell. I know the number of grams per mole of silver. A mole is 10 to the 23rd atoms. This is the volume of a unit cell. In other words, we estimate, based upon this, that silver has a density of 10.6 grams per cubic centimeter. Okay? So again, once we have all of these pieces of information together, this is now a macroscopic property determined by microscopic information. Okay, so let's make sure. So how many metal atoms are in a unit cell if the packing is simple cubic versus cubic closest? So cubic closest is face-centered cubic, 4 atoms per unit cell. Simple cubic is simply where I have the atoms on the vertices of the cube, one atom per unit cell. Okay, know how to go and determine the relationship between the radius of the metal and the length of the edge. Again, Pythagorean theorem. Very simple. Now, the band model for okay, let's end here, and I will pick up on my next lecture on the electronic structure and bonding in metals, and we'll talk about the bonding metal for a bonding model for metals. I'll go through a little bit of the details on this. It's a fun little calculation to show, and we'll talk about what's called the band structure and band model of metals. And one of the important concepts that's important is this electron C, or free electron model of electrons in a metal. So I will talk about that next week, and good luck, stay safe, and wash your hands, and remember to click like, subscribe, and to get an extra credit point, and we'll talk to you later.